continuing with the metal and iron system, if you recall the last lecture, what we have seen is strengthening mechanism. We have seen about effect of the grain size on strengthening, and we said that the coarse grain are actually fine grain structure is stronger, coarse grain structure is relatively less strong. Then we have some other strengthening mechanism that we were talking about. We just mentioned their names. Today we shall look into some of them. Alloying, intermediate second phase production is part of the same thing, and then we will talk about strain hardening and then effect of heat treatment on strain hardening itself. Then we shall look into the FEC system. So, we will introduce this FEC systems today, and then one of the major important product of FEC system is the steel, which is most commonly used, and of course, other one is cast iron and so on. So, we will look into that in the coming lectures, but today we will just introduce them. Okay, so, let us see what is the effect of alloying. We have defined what is alloying in the last lecture, and we said that you have another element coming into a host element. So, when we add an alloying element to the host metal, they may be present either in what is called a solid solution form or as an insoluble second metal or as a compound, right. So, it might either form a compound or might form sort of an insoluble second remain as an insoluble second phase, and then it might form a solid solution. Most often limited amount of solid solubility occurs in conjunction with a second phase. This is more common that you have a second phase, but a limited amount of solid solubility is also there. Of course, the most important is in all cases the introduction of the alloying element would actually cause slip planes, slip planes to be distorted, they get distorted, there is a change in the distortion of the slip plane takes because something new material has come in, and this causes distortion of the slip planes. So, when you want to now move or deformation has to take place, that is dislocations have to move, it has to move through the distorted slip planes, and this necessitates greater stresses, this requires higher stresses for movement of dislocation, thus greater thus it becomes difficult to have dislocation. So, what is it actually happening? In all cases distortion of slip planes occurs, necessitating greater stress for the movement of the dislocation, that means deformation becomes difficult. So, thus becoming harder. So, what you need, it actually improves the strength. So, alloying definitely improves the strength, that is the point, alloying improves the strength, because dislocation, movement of the dislocation becomes now difficult, movements of the dislocation becomes difficult because the slip planes have become distorted. So, and you need more stresses to ensure the movement of the dislocation, therefore, strength increases. Right. Now, as I said, they can go into form into solid solution. Now, this would depend upon the sizes, atomic sizes, the atomic radii of the two, the host and the foreign metal which has come into it. So, when it will depend upon the dimensions of the two. If the atomic radii of the two are similar, right, they are very similar, and they have, let us say, both have same structure, right, both have same structure like body centered cubic or face centered cubic structure or whatever structure. If they are of a similar kind of structure, then what will happen? They will just simply replace randomly. So, it will be random replacement, and it is called complete solute solution. So, you can see that when atomic radii of the host metal is similar, right, there, and the foreign, when these are similar, metal are very similar, this is the point. both have same structure, you remember we discussed about different structures, the arrangement in which atoms are present, because we said that they are spheres, they are in contact with each other and they have a specific arrangement, right, in the grains. And when they are, let us say, all are face center cube, both the host and as well as the replacing or the foreign alloying element which you have added, let us say they are of the same structure, then foreign metal forms random replacement and is called complete solid solution, because they are of the same kind. So, they will replace, it will replace randomly. So, this random replacement, and it will look something like this, you see, it will look something like this. I mean, if you look at this, if you look at this diagram, what you will see is, say this one, this already this white ones, the host metal, the blank white ones are the host metal, it was very much there, and then you have just the black one has come and replaced randomly, and there is no pattern, they have just replaced randomly. So, this is what is a complete solid solution. A complete solid solution would mean that the foreign metal, the second alloying metal which has come in, it has just, because they are of the same size, same arrangement, everything is same. So, they can just come and occupy one of the positions occupied by the host atom. So, that is what is called complete solid solution, right. All right. Followed from there, now this is all will not is all foreign alloying element are unlikely to be having same structure or the same atomic radii. There can be different atomic radii and different structure as well. So, you see, when you are trying to replace a host atom by a foreign atom, there is some energy imbalance, and this imbalance depends upon the atomic radii difference of the two, the host and the foreign element, right. Okay. When the radii difference is within 6% of one another, they are more or less similar, they are not same, but they are quite similar, within 60% of the radii differences are within 60%, not far too different, they are quite close to each other, not very far different, they are not same. Had it been same, then there would have been random replacement and it would have been a complete solid solutions. But this is, they are not same, right, but within 60% of each other, difference is 60%. Then the foreign element can go into the interstitial free space and is called interstitial solid solution. Then it can go into the interstitial space. If it is 60% difference, it would go into interstitial space. If it was same, they would have just replaced, randomly replaced, but here it is difference is somewhat less, let us say 60%, within 60%, right. So, it would go into interstices of the host element, and it will enter into a free space, right. Now, if we look at all metals in the periodic table, the larger size metals varying from cobalt to lead, most of the metal would be, there would be cobalt to lead, let us say. If we look at their atomic radii, they vary from 0.125 nanometer to 0.175 nanometer. Cobalt is 0.125 nanometer and lead is 0.175 nanometer. These are usually the host metal. So, if I have to have interstitial solid solution, then maximum difference I can have is the 60% radii difference. So, therefore, this radii difference corresponding to the 60% of 170, 125 and 175, these are the 60%, 0.075 and 0.105. So, 60% radii corresponds to this one. Therefore, anything within this size or any element within this size radii would actually can form interstitial solid solution with cobalt to lead, right. So, that is what it is, right. And if we look at, interestingly, we will see that the size that is we have talked about, that is 0.05 nanometer to 0.105 nanometer atomic radii, this atomic radius, this belongs to, this can just have only 6 elements, hydrogen to sulfur. So, these 6 elements have atomic radius of each of these individual ones falling between 0.075 to 1.105 nanometer. Now, carbon is included in this, because the group wise, if you look at it, carbon will be included in this, and that is why carbon can form, it can get into the vacant sites between iron atoms. So, if you compare the iron to carbon, carbon has a size which satisfies this criteria, that its size is not differing by more than 60% from the size, the atomic radius size of iron, and therefore, it can form interstitial, it can go into fills the vacant spaces between iron atoms and form interstitial solid solutions. So, interstitial solid solutions look something like this, interstitial solid solution looks something like this, it looks something like this. You can see that these white blank ones or the white colored ones spheres are the host element, and these black ones which have gone into the interstitial spaces, they are the foreign alloying element, and they have gone into the spaces in between. So, they have formed actually interstitial solid solution. So, this is what is interstitial solid solution, right. Okay. All right. The other variety is of course forming a completely intermediate second phase. Now, in this case, the difference of the radii between the two atoms, if it is too large, that is the host atom and the foreign alloying element atom, if their radii differences are too large, that is greater than 15%, but of course less than 60%, greater than 15%. So, they are not similar, they are quite dissimilar, right. The difference is greater than of course 15% and less than 60%, because 60% and above they will form interstitial solid solution. Now, this forms a new structure, they tend to form, the solution formed is new structure, and it is called intermediate second phase, because now they cannot get into the space between them, nor they can replace them. First one, when they are exactly similar, they would replace them, form random replacement, and we call them as a complete solid solution. The second one, in that case, if they are within 60%, the radius difference is within 60%, then we call it interstitial solid solution. But when it is far more than that, that means they cannot go into the interstitial space. So, they would remain separate and they would form a kind of second phase, and that is what the situation when it is large. So, this second phase formation, they look like this. You see, second phase formation would look something like this, right. This would look something like this. Now, you have the blank ones, these ones are the original host atom, and here they form a second phase somewhere in between. The original atoms are also here, and this one forms a kind of a second phase formation takes place in this zone. So, this is the third variety of effect of alloying, the kind of alloying that we have, right. Now, all this, what do they do? One thing we have seen, that whatever be the case, they actually distort the slip planes, and therefore, you need more stresses for dislocation to move, in other words deformation. So, therefore, they would improve the strength. Okay. Now, if the alloying element has the same hardness as the host properties, host element, then properties of the alloy is varied to a smaller extent. If they have the same hardness is similar, then of course, properties will be varied relatively less, right. But if you have harder one, on the other hand, if the alloying element is considerably higher hardness, affect the metal properties more. So, one issue is of course, one issue is related to what are the different types of alloying possible, that is what we discussed, and we have seen that in case of all alloying there will be some improvement in the strength, you will become more stresses, but their hardness properties, it's one thing is the atomic radii sizes, the other issue is of course related to the hardness of those material, and when the properties of the alloying element and the host element, if they are of the same nature, if the hardness are similar, then you are unlikely to find much properties difference of the final alloy. But on the other hand, if you have the hardness of the alloying element higher than the host element, then the properties are likely to be differing more. Okay. So, that is we have seen that, and this is another issue which we have seen, that important thing, in all cases distortion of the slip planes takes place, and therefore, more strength you are likely to realize in case of alloying. So, this is how alloying helps in improving the properties or strength properties, mechanical properties of the strengthening of the pure metal, strengthening of the pure metal, right. Now, the other process, other very important process of improving the strength of the pure metal or alloy system is what we call as strain hardening, and we are quite familiar with this because we use products which are strain hardened. We shall see that sometime later on. So, let us see what this process is. When you extend a metal, its cross sectional area will reduce. This is our common day experience. Supposing we take mild steel and try to pull it, it's if you try to let us say pull a mild steel bar, right, you pull it. So, the next stage what you do see that it has elongated, and there could be some sort of formation of neck, some sort of neck formation might take place, right, at some location, some sort of neck formation. So, its cross sectional area actually has reduced, cross sectional area reduces, right. So, cross sectional area reduces, it elongates and cross sectional area reduces. Okay. But it actually becomes stronger, and this process we call it strain hardening. So, area reduces, but its strength increases, and that is what we call as strain hardening. Right. In body centered cubic and face centered cubic metals, slip planes frequently intersect one another. So, the dislocation in one slip plane act as barrier to the dislocation trying to move across them. So, when you have combinations of body centered cubic and face centered metals, slip planes, in body centered cubic and face centered cubic metals, slip planes frequently intersect one another, such that dislocation in one slip plane act as barrier to the dislocation trying to move across them. So, that is what it is, right. So, dislocations are actually, because they are crisscrossing, they intersect with each other. So, they form as a barrier, right, barrier, since they are crisscrossing, slip planes are crisscrossing. So, they forms a barrier for dislocation, movement of the dislocation, right. Strain hardening therefore occurs as a direct result of dislocation source requiring higher stress to overcome this barrier. So, since there is a barrier, because they are crisscrossing, slip planes are crisscrossing, and therefore, dislocation cannot move, because dislocations move along the slip planes. That is what we have seen. When another slip plane comes and intersect, let us say, with it. So, this will act as a barrier for movement of the dislocation, and this barrier we have to overcome. So, when you have actually strained them, some dislocation has occurred at some point of time, it will intersect with some slip plane, and further dislocation will have to cross the barrier, right. Additional stresses will be needed in order to overcome this barrier, and that is why as the cross sectional area reduces, the its strength actually increases, because now some dislocation has moved, some deformation has taken place, some dislocation has moved, but it has actually now encountered another slip plane, right, crisscrossing it, and then when you want to cause further movement of the dislocation, that is more deformation, you would need more stresses. So, you need more stresses, and thereby strength actually effectively increases after certain amount of movement of the dislocation, right. So, this is the process of strain hardening, right. So, this is the process of strain hardening. Okay, let us understand it more. If you look at this diagram, it will make it more clear. If you look at this diagram, it will make it more clear. Right. Okay. You see, this is stress and this is strain. This is stress and this is strain. Now, in this region, this is what we have defined earlier as elastic region. If you remember, we have defined here as elastic region, where basically stress strain is linear, and if you release, this will come back. So, what happens during this region? Dislocation networks stressed, just stressed, and elastic non-permanent deformation. So, though no movement of dislocation has actually taken place, it is only stretched, it is only stretched, and if you release it, if you release this, if you release the load, if you release the load, when you release the load, what will happen? It will come back to its original position, because it is only stretched, there is no movement of the dislocation that has taken place. Now, when you go further, actually what will happen? Plastic deformation, dislocation, nucleates slip in the adjacent grain. So, therefore, dislocation actually starts moving, right, and it will of course, this is specific for a specific sort of structure. So, dislocation has started moving. Now, as you further move out, dislocations are entangled, resulting in a network, resulting in, of course, work hardening, because as you move further, first this portion it is simply stretched and nothing more. In this zone, it is now dislocation has moved somewhat, but as it moves further, there is some position where dislocations will get entangled, because the other slip planes will come and intersect with it, and therefore, you have to actually overcome that barrier, and that's why there is a work hardening. That's what is work hardening, right? That's why there is work hardening. Okay. So, that is the idea of work hardening, strain hardening as we call it. So, this is diagrammatically again shown here, as you can see. This is diagrammatically shown here. You see, as in this axis I have percentage reduction in the cross sectional area during cold working. So, when actually we achieve this strain hardening by cold working, it is in all cold state, not in hot state. If you have it in hot state, then obviously you will not get this effect. So, in cold state, as we shall see later on, So, it is cold work, this is important, because this is commonly used reinforcement bar. One of the types are cold work or cold twisted deformed bars. We shall discuss about this sometime later on, but supposing somebody gives you hot, same thing, hot twisted hot work bars, they are not going to give you the same property. So, we do cold twisting, that is strain hardening is done by or cold working, or applying stresses at the cold state, no temperature change. So, that is what we are actually working onto it and giving some permanent deformation. So, this side gives you permanent percentage reduction of cross sectional area during cold working. So, when you are cold working, trying to pull it or do something or some sort of cold working you are doing, the percentage cross sectional area reduces, right. So, this is, as you say, cross sectional area reduces along this one. So, as the cross sectional area reduces more and more, what you find is the tensile strength increases, because we have understood what is the phenomena, how it is happening, we shall see this actually. So, tensile strength increases. So, that is what we stated first, right, tensile strength increases, but what we see is the available percentage elongation also reduces, We will come back in a minute here. This side, this axis is tensile strength and this axis is percentage elongation. We will come back in a minute here. Let us look at another diagram. You see, this would show you, better the idea. This side is strain and this side is the stress. Now, this is my original stress strain diagram, right, diagram, and this is original stress strain diagram, and this side this is this is my original before I have done anything. Now, when I, let us say, apply stress and reach at this point F, when I reach this point F, right. So, what will happen, the dislocation have now actually entangled, many of the dislocation has got now entangled actually. So, when dislocation is entangled, actually, so you will have increase in the stress required to cause further dislocation. So, that is the idea. So, what happens when I have gone up to this, and let us say I have released it, So, it would when I have released it, this is the OE is the permanent deformation that I have given. We have gone up to F and I have given OE permanent deformation. So, when I next test or stress it, right, what will happen? It will actually go somewhere up to G, because the dislocations have actually entangled, the cross sectional area is reduced and dislocation have actually got, many of the dislocations have got entangled. So, you have to cross that barrier and actually you might have an increase in the this effect or useful stresses, or Z will shift to G. So, this process is simple work hardening in this zone, and this is further if you just bake it for some time, and then this is what you will get it. So, what will happen in the process? Of course, your deformation or elongation will reduce. Original elongation available was this much, now the elongation will reduce, and therefore, percentage elongation there is a reduction, percentage elongation there is a reduction, and that is why in case of strain hardening that you find that your strength increases, useful strength increases, but the available ductility reduces, that we have defined ductility earlier, available ductility reduces, right. So, that is strain hardening. Supposing I apply heat on strain hardened material. Now, when you have done strain hardening, you have actually areas where you have got higher strain, areas where I have got higher strain. There are regions where there will be higher strain, and this will not be thermodynamically stable, because you strain something, it would like to release, you have actually stored some energy there and it would like to release that energy and come to a stable state. So, this is not thermodynamically stable. Therefore, this dislocation area that you have created after strain hardening, this is not stable. So, if you give a little bit of energy, would mean that it will come back to its original stable state, it would like to be in an unstable state. So, small amount of heat can it can cause redistribution of this dislocation array with heat, and that is what happens. Now, this response to heat of work hardened metal could be three kinds. It can be a recovery, a recrystallization, or lastly what we call annealing. Recovery, recrystallization, or annealing. Recovery, recrystallization, and annealing. What is recovery? In case of recovery, which takes place up to about 30% of the melting point, right. So, up to 0.3 temperature. If the temperature is 0.3 multiplied by the melting point, then what happens is dislocation entanglement decreases, and structure becomes coarser. But as the dislocation density remains same, overall hardness and strength remains almost same. Recovery is little bit, what happens is you just heat it up to 30% of the melting temperature. Now, when this is happening, it's dislocation entanglement which you have done during the strain hardening, it would get somewhat reduced or decreased, and therefore, the structure would become coarser. So, you will have, since dislocation density still remains same, overall strength would still be nearly same, almost same. And this has got a relevance, as we shall see in case of let us say fire affected strain hardened material or metal, strain hardened metal. Up to certain temperature, right, you do not see much of an effect onto the structure, because this is simply belongs to recovery. But beyond that temperature, there are changes that take place. Let us see what are those temperatures. If you go up to 0.5 of the T, if you go up to 0.5, that is 50% of the melting point, 50% of the melting point, we call this temperature as recrystallization temperature. This causes further reduction in degree of dislocation entanglement. So, as you obviously the effect of the temperature or heat is to reduce down the effect of dislocation entanglement, which has caused actually strain hardening. Now, as you go to higher temperature up to 30%, all right, there will be some reduction, but you go further higher and there will be more redistribution of those entangled entangled dislocation that is there. There is a because the slip planes, because the dislocation get entangled, so that entanglement would get further reduced, and this will result in what? This will result in grain boundary angles change, because the dislocation entanglement that has occurred because the slip planes are coming and intersecting with each other, and now you have supplied heat, and this because we said that heat can actually, this is an unstable situation, the heat can redistribute the whole thing, and this causes actually grain boundary changes because of formation of new grains. This causes formation of the new grains and grain boundary changes, this grain boundary changes. So, this grain boundary changes softens the material, grain boundary changes causes softening of the material, and now atomic diffusion becomes possible, strength and hardness decreases. So, as the recrystallization takes place, strength and hardness would decrease, strength and hardness would decrease. So, therefore, what we see, first we have some temperature up to which actually there is some temperature up to which there will be some disturbances in the strain hardening, some disturbances in the strain hardening. This is about 30% of the melting point. So, there will be some disturbances in the strain hardening, but not much change in the properties takes place. But beyond that, as you go on increasing the temperature, recrystallization up to a temperature which we will call recrystallization temperature, right. So, above a temperature called recrystallization temperature. So, beyond 30% of the melting, if you heat up to 30% of the melting point you heat, there is no problem. Beyond 30% of the melting point, there will be some little bit disturbances, but strength would not reduce significantly. But beyond 50% of the melting temperature, if you heat, then there will be recrystallization, and this recrystallization means new grain structures are forming. So, since because now it is almost in the molten state. So, recrystal, because you have given heat, so actually the grain formation, new grain formation would take place, and these new grains would alter the original grain boundaries altogether, and there could be coarse boundaries, coarse grain formation, and the structure will be now coarse, and that will result in actually softening of the metal itself, and therefore, there will be some amount of reduction in strength, and as well as hardness. Okay, let us see what happens beyond that. Supposing we heat it beyond this temperature, temperature, what is known as further beyond this, the annealing would take place. So, up to certain temperature there is not much disturbances, further beyond this temperature there will be reduction in strength, and still if you go on heating further above this recrystallization temperature, then much higher above the recrystallization temperature, then what happens is there will be redistribution of all the dislocation entanglement. So, new structure formation would take place, and this new structure formation would result in actually what we call annealing, and it is complete redistribution of dislocation. Grains become much bigger, because now new formations would take place, new grains would form, and this becomes much bigger, and therefore, there is a reduction in the strength. There is a strain hardening is, and after complete annealing, actually total history of annealing is erased. So, effect of of strain hardening is erased. That means, by annealing you can completely bring back, not bring back, you can all the positive effect that you got due to strain hardening, that would be lost, and you will be having now a much coarse grain structure, and would actually will be you will have a coarse grain structure, and you will have a weak structure. Actually, the strength of the metal would be much less. So, that is what is the effect of heat on strain hardening. Annealing is the process whereby actually you are removing the effect of the strain hardening completely. If you want to remove the effect of strain hardening completely, you just do annealing and it will be totally removed. Hot working, of course, above recrystallization temperature in not strain harden. Otherwise, supposing you have a metal and then you start working onto it, hot working at above recrystallization temperature, both deformation and recrystallization will occur simultaneously. You are working onto it hot, so both deformation and because you are applying stress and recrystallization will take place simultaneously. So, it is much easy to work at higher temperature, because since you have given some heat, you know, the energy has been supplied. So, the dislocation movement becomes easier. You can work, I mean, it is softer, it is now much softer, the structure is much softer, and therefore, you can work onto it easily, and recrystallization also would take place simultaneously, therefore, resulting in similar structure as as above, that is similar structure as the annealing, you will resulting in similar structure as annealing. So, hot working above recrystallization temperature, deformation and crystallization occurs simultaneously, resulting in same sort of structure formation as the annealing structure. But obviously, it is not going to give you the strain hardening. So, hot working is definitely not going to give you strain hardening. In fact, it will give you much lower properties than what is obtained through strain hardening process. Right. This can be explained easily through this diagram. As you can see through this diagram, effect of annealing. This is the annealing temperature, and this is the tensile strength. So, as this is my recrystallization temperature actually, right. So, as I increase my temperature beyond this, the annealing temperature beyond this, tensile strength reduces. So, it goes back to a quartz grain structure, and therefore, the tensile strength is reduces, but the percentage elongation of course increase, that is the elongation that would be available before failure is increased. So, what has been done, actually strength has now reduced, strength was much higher before, but it had lower ductility. So, once you do annealing, it is actually percentage elongation increases. So, ductility is recovered, ductility is again available, but strength is now reduced, right, percentage elongation of course in this axis. So, it is now increased as beyond this temperature. So, that is the effect of annealing effect is something like this, right. So, having seen some of those strengthening mechanism that we have discussed, basic strengthening mechanism, now we can look into iron carbon system. This is the most commonly used alloy in construction or civil engineering industry, or even in most of the other industries. Now, you know, pure iron is not very strong. So, we use it mostly as ferrous alloys. As you can see, we use it mostly as ferrous alloys. Now, you can add various kind of elements, can be added, and they have different effect on the strength, right, because we have seen so far one thing is the atomic radii. So, depending upon the atomic radii, some of those elements which you add in alloying would have one kind of effect, some other element will have a different kind of effect. So, each various elements added has different effect on the strength of the ferrous alloy, right. So, let us see what are the effects. So, if you look at this diagram, we can see that what are the different elements, how do they affect, how different elements affect. For example, if you choose carbon, this is the weight of the solute, right, means the alloying element that you have added. Iron is the host. So, supposing 1%, 2%, 3%, 4% weight of the solute that you have added to iron, right, various solutes, and this is the yield stress. Now, if you see, first one is the carbon and nitrogen. So, if you add them, if you add carbon, then it shows a very increase, little bit percentage addition increases the yield strength significantly. This in MPa increases the yield strength significantly, whereas you do not have anything, it is pretty soft material, Phosphorus, this does the same thing, it also increases the yield strength as we increase. Silicon does the same thing, manganese, titanium, aluminum, nickel, molybdenum, tungsten and vanadium, cobalt and chromium. So, you see out of all this, carbon does the trick most. Basically, it actually it increases the yield stress maximum, and among them chromium does least, but phosphorus, silicon and manganese, all of them go on depending upon their percentages, they go on increasing the yield stress of the alloy, yield stress of the alloy, right. So, therefore, carbon Fe system, and we have also understood that it forms an interstitial solid solution, it forms an interstitial solid solution, right, because the atomic radii of iron and carbon are such that it can form interstitial solid solution, and that is what is the background, and that is why carbon iron system is used most often. And you know, the steel which is most commonly used, or cast iron, these are all belong to iron FeC system, right. Most important of all alloy is FeC, and let us look at its behavior a little bit. To understand this, we will look into what is called its equilibrium diagram. Now, in this process of most important of alloy, that is FeC system, we add actually to the soft iron, we actually put a hard carbon. So, we said the sizes, atomic radii are within 60%, and iron is quite soft, and we add hard carbon. That is why this is, because the previous diagram that we have seen, carbon is the one which gives which improves the yield stress most at a least percentage compared to anything else. Therefore, we add carbon. Soft iron is improved by the addition of carbon, and you know, that is why we get most benefit, right. And this arrangement of the phases may vary depending upon the cooling condition and heat treatment. So, you actually in solution form, in liquid form, molten form, you add this, and this phases that they form, it may vary depending upon cooling condition and heat treatment. Some cases extremely hard metastable phases are formed as a result of heat treatment. So, let us see the equilibrium diagram of iron, which will give us some idea regarding the same, and we will continue to see it more in some of these effects in the next classes, so that next lectures, so that we can understand it better and see, and also see their usage in our construction industry. This is what is the equilibrium diagram of FeC system with 6.7% of C, 6.7% of C, with 6.7% of C, right. Now, if you see in this diagram, first of all you will see a region where you see alpha, this is alpha, this is the region, this is the region where you have got alpha iron, you know, this region, this small region where you have got alpha iron. This is stable below 910 degree centigrade, this temperature is 910. So, it is stable below 910 degree centigrade, and this alpha iron has got a body centered cubic structure. When you have got very low percentages, say up to 0.025 percentage of carbon, very small percentage of carbon, this forms a interstitial solid solution. As we said, the atomic radii differences are within 60%, and therefore, carbon can easily form an interstitial solid solution, and when its percentage is low and up to 900 degree centigrade, you know, it forms this sort of solid solution. Well, in this diagram, of course, as you can understand, this is all liquid, because all this equilibrium diagram, top form is liquid, this axis is temperature, this axis is a percentage of the alloying element, this axis is temperature. So, as we cool down, we come vertically downwards, as we cool down, we come vertically downwards, and as I go in the horizontal direction, the percentage increase in the alloying element takes place. For certain elements, you can draw the complete diagram from 0 to 100%, but our interest is not there in that one. We are only looking at iron carbon system, which is the most popularly used construction metal in or alloy in construction. So, therefore, that is why we are looking only at this one, and all these are liquid in the beginning, as you can see at high temperature. As you cool it down, this solidifies, and then we will see that each diagram, and this, for example, this portion, as this, you know, this is inclined along this direction, because as you increase the percentage of the alloying element, there is a depression of the melting point. Melting point depression of the melting point takes place. This would be possibly pure iron would be melting here. So, this as you add carbon, the liquid it is the liquid pure liquid line. If you draw lines, I mean if you draw the cooling curves, you will see that at this point with this much percentages, this at this temperature it solidifies, or rather solidification starts. So, here you will have some solid and liquid, some solid and liquid, and at this point of course, all are below these are all solids, below these are all solids. So, this line is the line of actually solidification. This is the melting starts melting, I mean solidification starts here, solidification actually finishes along this line. But depending upon the temperature of cooling, different products are formed. So, let us first look at each of these products and some idea about what kind of structures they have. So, first one I was talking of is in this zone below 910 degrees centigrade up to a 0.025, this would be 0.025, this point will correspond to 0.025 percentage of carbon. You have a body centered cubic structure known as ferrite or alpha iron, right. Okay, known as ferrite or alpha iron, right. It has got a body centered cubic structure and it forms an interstitial solid solution. Let us see another one. Above this 910 degrees centigrade, in this zone, you can say in this zone, what is formed? Iron actually in this region, when you are cooling from here, it undergoes a polymorphic change to face centered cube. So, it was body centered cube in this zone, here it is all face centered cube. It is all face centered cube and it is called austenite or gamma iron, it is called austenite or gamma iron, right, capable of dissolving up to 2% carbon. So, if you see that this point is 2% carbon, so it is up to 2% carbon can be dissolved depending upon of course, the cooling temperature. So, as you arrive at like up to 2%, you will have, if you come from this side, from here you cool it down, you will reach to this. So, maximum 2% carbon you can see in austenite or gamma iron, austenite or gamma iron, right. Okay. So, these are the two phases. Let us see some more of these phases that forms in case of, right. Continue with the same thing. Above 1400 degrees centigrade, further polymorphic change is taken place and you can see here there is something called delta. So, somewhere around this, I mean further polymorphic change results in structure of delta iron. So, here it is somewhere 1400 degrees centigrade, above 1400 degrees centigrade you will have delta, and this is again has got a body centered cubic structure, it has got a body centered cubic structure. So, you have alpha, gamma and delta here, right, you have delta here, okay, right. So, above 1400 degrees centigrade this delta iron formation takes place. Let us see what happens on the right hand side. Okay, we will come to that, but at the moment let us understand. So, we have seen three phases, alpha, gamma and delta iron. These three phases are all soft ductile phases, they are all soft and ductile phases, they are not very strong, they are quite soft ductile phases. So, these three are ductile phases. You can see some more zones, for example, this zone is alpha plus gamma, this is pure gamma, right. This is gamma plus liquid, because as it is cooling, gamma iron plus liquid formation takes place, and we will come to this phase now next. So, these are all soft phases, and but ductile phases. If you look at same diagram again, at this end 6.7% or containing 6.7% carbon, this is not 6N, this should be 6.7% Fe3C, and this zone, cementite or iron carbide, and compound formation takes place. It is an interstitial compound of iron and carbon containing 6.7% of carbon. In this formula is Fe3C, Fe3C, as we have written here, Fe3C. So, at 6 point, at this point 6.7% carbon, it can contain about 6.7% carbon. You have a formula Fe3C, a compound is formed. So, we said that while alloying that there could be intermediate second phase or compound formation. So, this is the compound Fe3C forms at this range. So, you have liquid formation, here liquid plus Fe3C, and here gamma plus Fe3C, and this is alpha plus Fe3C formation takes place, right. So, let us see what are the properties of this Fe3C. The properties of Fe3C is extremely hard and brittle. This is extremely hard and brittle. So, this is extremely hard and brittle, this is extremely hard and brittle. Now, one important point is this point E, one important point is this point E. You see, at E, eutectic reaction occurs and this austenite solid solution reacts to form fine laminated mixture of ferrite iron and iron carbide. So, at this point reaction occur. I have not defined this, so does not matter, but what we understand is for our purpose that the austenite solid solution reacts to form a fine laminated mixture of ferrite and iron carbide. So, at this point ferrite and iron carbide, ferrite and iron carbide. So, fine laminated structure of ferrite and iron carbide, that is what formation takes place. So, this is what is a useful phase diagram for our purpose. Let us relook at it again. We said this carbon is a, relook at this again. We said that carbon is a hard element compared to a soft iron. So, we can actually in alloying carbon can be used, and we have also seen that its radius is within 60% of the iron. So, therefore, that is why carbon is used, and then second, then we have seen that it gives the highest yield stress amongst all the alloying element, right. So, coming back to this, when you add very small percentage of the carbon, that 0.025% up to this 910 degree centigrade, we have this alpha or ferrite iron. Above this temperature we have gamma or austenite, and above 1400 we have delta iron. This has got a body centered cubic structure, this has got a face centered cubic structure, and this has again got a body centered cubic structure. At the when we add 6.7% on the higher side, this percentage of this percentage 6.7% of the carbon, you have Fe3C, and in this zone you have got liquid Fe3C, in this zone you have got gamma Fe3C, and then here the reaction at 0.85 C at E, the reaction eutectic reaction takes place, and which gives us a fine laminated mixture of ferrite and iron carbide, and that is what we are seeing here, that is what we see here. Here is gamma plus Fe3C, and that is what is a phase diagram of the or equilibrium diagram of the FEC equilibrium diagram of FEC system. Now, this will help us in understanding the behavior of iron and the types of iron that we use, or behavior of iron C system, that is steel, cast iron, etc. It is quite often it is asked, for example, the code specifies certain maximum amount of carbon for, let us say, MS steel or steel to be used in particular usage. Now, if you know why it is, this sort of equilibrium diagram will give us understanding of why such restrictions are imposed by various codal practices, codal practices for various kind of steel that we use in certain construction practice. So, with this I think we can now summarize today's discussion. So, what we have done, we have looked into various strengthening mechanisms, right. If we go back a little bit further, first we have looked into the grain size, its effect on strengthening. We have seen that coarse grain tends to give us lower strength, and compared to fine grain. Then we have looked into the effect of alloying. Normally alloying would give us higher strength, and then we have looked into effect of strain hardening, which we have said that it can give us higher strength. But on the other hand, if you heat it up to certain temperature, of course there is no problem, there is not much reduction in the properties, but if you heat it up further, then there will be reduction in the properties, and if you further much beyond recrystallize, I mean if you further above beyond recrystallization temperature, the crystallization will start, and therefore the whole effect of strain hardening will be lost. Quite often we use strain hardened steel in construction practice, but as you can understand, when you subject them to fire or heat, their properties would be they lost their properties, and that has got the relevance because steel is normally supposed to have poor fire resistance compared to many other material, namely the other construction material. I mean, in comparison with other construction material such as structural construction materials such as, let us say, concrete or even reinforced concrete. Right. So, that is what we have seen, and then we have looked into the structure. We have looked into the structure of the FEC system. What we said is this the different types of phases that form, and we have seen in small percentage of carbon up to 910 you have alpha or ferrite, and above this up to 2% carbon we have seen that we have gamma or austenite, and we have delta around 400, but on the right hand side with 6.7% of carbon we have Fe3C formation, and at lower in bulk of the at higher percentage of carbon we have seen Fe3C with alpha ferrite combination, etc. So, I think with this we can now look into various properties of the steel and cast iron, etc., types of steel and their usage in civil engineering, construction practices, and performance in service in the next lecture. Thank you. To conclude this lecture.